All right, so welcome to track 2, session 2. And now I have Kazem with us. He is a staff ML engineer at Course Hero, working on their recommendation systems and also the search engine algorithms. And he's going to share a story on semantic search at Course Hero. So, stage is yours.
Thank you. So yeah, can you guys hear me? Okay. So the topic of this talk is going to be semantic search. Course Hero is I don't know if you guys ever use Course Hero. It's an education tech company that students go to the websites. This is loud. Students goes to the websites in order to get help with their, let's say, with their courses. So let's say if you have exam coming, you can go to Course Hero. We have is a marketplace. We have in order of hundreds of millions of documents, like problems on different university subjects like mathematics, economics, and so on and so forth. So you can go and, let's say, before your exam or before your homework, see sample problems or see some kind of notes from the other students from your course that they have uploaded on Course Hero, and then prepare for basically your course. I'll demo something so you guys have a better understanding of the problem. For this talk, I'm going to going through 3 topics. The first part, I will define the problem, the semantic search problem. I give a more formal definition of the problem. And then I'll talk about the latest research that has been done and we have leverage at Course Hero in the semantic search space. Most of my talk is focused on NLP side, less about the search space, but NLP obviously is a key part of the semantic search. After that, I talk about some evaluation that we have set up and some optimization that we did last year on our embedding models and the A/B test that we ran. And the third part is, which is the kind of state of the art, is that how one can fine-tune, let's say, a language model, a transformer model here, Sentence-BERT. And at the end, we will wrap up what is kind of the state of the art, what is our plan for 2022 in terms of semantic search. And yeah, and we are hiring. So if you guys are looking for search or ML or NLP positions, we have lots of data, we have scalability problems, lots of problems that you guys can come and tackle. So please come and talk to me or apply directly. So I like demos. So let me demo something first. So this is a Course Hero website. So if you guys, and one of the major features that we have is the search. And our search is basically 2 pieces. One is the federated search, which I'll call it the lexical search, the traditional way of search. The other one is that we launched it like 3 years ago, is the semantic search. So you as a students can go to Course Hero and then ask, what is mitosis? And what happens when you do that search, this is the search results. So in parallel, we run 2 search engines. The first engine that we run is the semantic search at Course Hero. And here you see that basically we match your query with a question that has been uploaded at Course Hero index database, which is the same question. So you can unlock that questions and then kind of find how other students have solved that problem, let's say that mathematical problem, and get explanation. So lots of revenue of the company comes from this feature, which is based on semantic search, and that's why it's important. And if you think about the Let's go to the slides. Yeah, so now the definition of the semantic search. So essentially you have an index. In our case, we have in order of right now, I think 200 million questions in our index. Semantic search index here, whatever I talk here is not about the lexical search, it's about semantic search. So we have 200 million of questions on 40 subjects, as I said, like mathematics, computer science, and so on and so forth. And the semantic search is essentially the problem that we try to solve is that when a user comes and type a query, if we detect the intent of query is a question, then what we do, as you see on this snapshot, what we do is that I don't know how does this work. What we do is that we basically match your query with our index of questions, and we find the most similar questions to your query, and that's how we unstuck you. The focus of this talk, again, is going to be the embedding model of semantic search. I'm not going to talk about the nearest neighbor and those kind of technologies. And embedding model, if you guys think about embedding model, in the semantic search, the core algo is essentially the embedding model. And what does that mean? It means that how you guys take a question and embed it. So a question is basically a text. In our case, it could be a paragraph. So how do you take a paragraph and turn it to a vector in this d-dimensional space, a dense vector? In terms of metrics, we have two types of metrics. One is the ML metrics that we have. Our ML metrics is mean average precision at k and recall at k. This is how we kind of test different models offline. Or obviously is the purchase rate or conversion rate, how much people are unlocking that card that I just showed you guys, which is kind of a proximity for recall. So those are the metrics we track online when we run A/B. This is this is very simple drawing. So I made. So this is basically the architecture that right now we are using for semantic search at Core 0. This architecture, we have been using it for almost 3 years now, is in-house implementation. If you guys, I don't know how much you guys know about the semantic space. It's a very new space. So 3 years ago even, there were not any, lots of these vendors that they show up, they were not there out there. So we had to come up with our own in-house solution. Our semantic search is built on top of Elasticsearch. So we use Elasticsearch as basically the main engine to run semantic search. So essentially what we have is, we have this pipeline that you guys see on the left. We have these questions that what we do is that we have 200 million of questions, and then for each question we compute the embedding using the embedding algo, and we compute that, let's say, using whatever nearest neighbor we use. We are using LSH, linear local sensitive hashing. We compute the hashes of that vector, and then we store these vectors and hashes in Elasticsearch as index. So that's how basically we compute the index. Keep in mind this index also is kind of a real-time index because we get like 50,000 of questions every day, so we keep adding to this index. One major problem that we have is that how to solve this problem at a scale. So when you want to compute the embeddings for 200 million of questions, scalability is a huge challenge. The second part of the semantic search is the service. So we have a real-time service, microservice. What that does, which is very simple, is that when a user comes to the search and they type their query, we intercept that query. We compute the embedding of that embedding vector for that query. We compute the hash for that query. And then we have our own plugin implemented Elasticsearch, and we use that in order to run nearest neighbor on Elasticsearch. So we kind of got ahead of Elasticsearch. I think Elasticsearch is releasing the vector similarity probably last year. So we kind of did this 3 years before even they get to that point. So when we do, when we run our plugin, then we get, let's say, 1,000 candidate for that particular query. Then we brute force sort them based on their cosine similarity, and then we return, let's say, for these features that I showed you guys earlier, the top result. Yeah, so that's like, one thing that I had. I think I will cover that part. So I don't know how much you guys are familiar. So I assume not many people in Search conference are familiar with this latest work that has been done with NLPs. That's why I just brought this slide. So there is this paper published in 2019 called Sentence-BERT. If you guys think, if going back to 2017, we have transformers. After that, we have the introduction of BERT, which got incorporated in Google Search, like I think 1 year ago, and that really impacted the performance of Google Search. Why? Because the problem with the lexical search is that you kind of matching at the token level, but if you do the token level, let's say TF-IDF or BM25, you will lose the semantic of the query. What with transformers we are trying to do, we are trying to capture the semantic of the question. And BERT kind of was one step in that direction. But the problem with BERT is that you cannot naturally use BERT to compute an embedding, let's say, for a sentence or a paragraph or a document. Those are the problems that we are solving. So what happens is that this paper, what they did, they used this architecture that you see on the right, which is Siamese network. Is an old architecture used in image space. Essentially, what you do, you have a training set of data. You have a collection of pair of sentences, and you have labels for them. If a pair of sentences are semantically similar, the label is 1, and if they are not, 0. So you feed this to this architecture, and you are trying to basically map similar questions or similar sentences in that d-dimensional space in the same location. This paper actually showed that the quality of using these models is way better than, I don't know if you guys tried BERT, but compared to BERT, you can get a boost of 30, maybe 20, 30% if you try to use BERT in order to compute embedding for a sentence. So I encourage you guys, if you're interested, check the paper. So last year, I think until November, we were using this old paper from Google called Universal Sentence Encoder, 2017-ish or 2018-ish paper. And what I found was that our goal was to see how much we can improve the coverage of that feature that I showed you guys earlier. Getting users showing the users the right questions, and then help them, and then increase the revenue. And so one thing that I was working last year fall was that what embedding model we can use instead of use in order to improve the performance of what we have on production. And that's how I got to finding that paper like last summer. And then this diagram, this table shows that some of the offline benchmarking that we did. And basically, you see on, it shows map at 1, 3, and recalls at different k. And what we found is that if you look at the last row, we saw a huge improvement at the map at 3 compared to what we had on production, which was use plus LSH. So the precision, mean average precision at 3 kind of went from 0.62 to 0.76. So this was, I'll explain some of this, how we did this offline analysis. And I think that the nice thing about that offline analysis is that for the folks here is that with our setup, you can, because you cannot run A/B tests very fast. Every A/B test that we run, it takes like 4 or 5 weeks, so it's slow. So, but if you run this offline evaluation, you can do much faster. You can iterate way faster. After we found SPERT performs better than use, in offline or in our lab space. We went ahead with the AB. And our AB also showed the same thing. We saw for the same conversion rate. So the use was the control version and SBERT was the variant. When we ran that AB, we saw 32% improvement on the coverage. So basically 32% boost in the revenue. That's why it matters, okay? And that's kind of goes back to my earlier point that the core of the semantic search is the embedding model. One thing I wanted to say is that in terms of scaling, what I found working very well, our old pipeline of generating index was based on Apache Spark. We're using Apache Spark for use v3. But what I found is that Spark doesn't work very well for SBERT, SBERT being PyTorch kind of embedding model. But I don't know if you guys have tried Amazon Batch Transform. I found that much more cost-effective, maybe 100 times faster than Spark. So that's something for you. And obviously, you can use GPU, which helps a lot with this embedding calculation on Batch Transform, Amazon Batch Transform. So that's one. Yeah, I put this slide to kind of this was the big things for us when we want to basically run our evaluation offline. The first question is that, I think the previous talk, I don't know if you guys were here, the whole talk was about how to create judgment list. Okay, he was trying to show, how can we create a judgment list using our click data? So that's key, that's the first step. So if I want to start, first I have to define, if I want to do any ML work, the first, define your metrics. The second part is that what is your evaluation? What is your test judgment list for benchmarking? And luckily for us, or for you guys, if you guys are trying to do semantic search work, Quora has a data set, which is great for some of the problems, at least for our use case. So Quora has 400,000 of question pairs labeled by human. This is the interesting part, because they got the human to go through the pair of questions that they had, and they could label, let's say, a positive pair example you see. How do you start a bakery? How can one start a bakery business? They label this as one, meaning that they are kind of duplicate. And then the negative pairs, another example that is kind of what are natural numbers, what is a least natural number. So if you look at the negative pair, is an interesting one, because still the topic is the same, but they are not semantically similar. It's kind of, this seems obvious to human, but to machine is not obvious. If you want to create, let's say, the data set using a programmatic approach. So anyway, we use the Quora data set. Here I explained that how we use the Quora data set in order to create a judgment list. We sampled 12,000 of the questions from Quora data set, and then we built a semantic graph, and then that was our basically test set. And we use this for basically benchmarking most of the semantic search, embedding models, and some other vendors that we want to benchmark. This is, so yeah, these are, so you guys can go and check it. But the Sentence-BERT model that we used last year was the paraphrase MPNet model. Last year, there were just very few models that these guys released. Right now, if you guys go to Hugging Face, there are much more models, pre-trained models that has been released. That was not the case last year, summer. But we kind of launched the paraphrase MPNet-based model, which was a Sentence-BERT model on production. The dimensionality is 768. One thing to keep in mind that I noticed that later while I was working is that the maximum sequence length that you can fit to these models is, there is a bound. For example, for this particular model, it only consumes 512 tokens. But that's something you guys, I think, it matters if you want to go to production. Yeah, I'm not going to cover this, but these slides will be available so you guys can go through this. So essentially, this table shows the first kind of experiments that I was running manually, and I saw use v3 was kind of BS kind of embedding model in terms of the cosine was super inflated, and that was the main observation that made us working on replacing that. Keep in mind, use has transformer models as well. Use v3 is a deep average network. That's why it's faster, but the accuracy is lower. But if you guys want to stick to use v4 might be a better architecture. The last part of my talk is basically how much time we have?
Oh, 20.
Okay. The last part of my talk is going to be, lots of this pre-trained sentence-BERT model has been trained using the web data. For example, the Quora dataset is one dataset that they use to pre-train their models using that Xiaomi network that I was showing you guys earlier, this architecture. So basically, this is how they train different sentence-BERT model. They use, let's say, Quora dataset, Stack, some questions from Stack Overflow, I think, Yahoo, and so on and so forth. The problem with those dataset, obviously, is that they might not represent your domain. Our case is that edtech, so we have mathematical problems. So lots of these math symbols are missing, but those tokens are in our queries. So if your model hasn't seen those, so it's not what's going to happen. It's going to mask or kind of ignore those tokens. So essentially what we wanted to do, we wanted to see how can we improve the sentence-BERT model. What is the next step? And this is kind of gets to the you don't see much literature on this space. There is some work, but the works are really shaky, what I have seen so far. And there are not that much industrial proven work. But what we try to do, we try to take one of these sentence-BERT model and fine-tune it with our own data set with 40 subjects, university subjects. This graph shows our offline evaluation of fine-tuned model, which is the orange one versus the original SBERT model on the test set. And you can see there is a sacrifice on precision. So when we fine-tune, the precision drops, but the drops is not that significant. It's if you look at the y-axis, which is precision, is at the range of 0.005. But there is a sacrifice on precision. But if you look at this is the interesting part, if you look at the recall, and that was kind of our goal was to improve the recall while keeping the precision kind of constant. When you look at the fine-tuned model recall, you see that the orange has a huge boost. Keep in mind this x-axis is the threshold, the cosine similarity threshold. For example, to up to 0.8 cosine similarity, the fine-tuned version outperform the baseline. And that's because of the language, that you kind of train the SBERT with your own language. So this effort will happen in Q1. And we ran, based on those offline analysis, we did an A/B in February with a small index. So we A/B tested the SBERT fine-tune versus the SBERT baseline that we shipped last year, which is the paraphrase MPNet model. We kind of did some calibration before running A/B tests, meaning that we used two different thresholds for the both model. Keep in mind, every time that you use a different embedding models, obviously the scores, the cosine similarity scores, is going to be different due to the nature of the training and such. So we use the 0.99 threshold for fine-tuned version and 0.92 for the control version. And I didn't expect that the lift on A/B. I was kind of a bit surprised. My expectation was lower, but it seems that it's working. And to my knowledge, I haven't seen anyone I have seen people talking about fine-tuning and shipping that to production, but I haven't seen anyone kind of showing their results, at least at the industry. So that's kind of early results that we got, that fine-tuning seems working. And for fine-tuning, this is not the only way that you guys can fine-tune. There are very different ways that you can fine-tune sentence-BERT model, but this is the approach that I took. So I used the Xiaomi architecture again, as you see. The main challenge when you want to guys fine-tune is obviously creating the training data. That's the tough part, because this is supervised approach. So for sampling similar questions, what I did, I went to history logs, and for every pair of query that the user have put in our search, if they bought a question, let's say if they unlocked the questions, I sampled them as a positive pair. I did this sampling across 40 subjects to make sure that the distribution of the sampling across subjects is uniform. And for the negative part, negative pairs of questions, my approach was naive a bit. I did the random sampling within a subject, but although the random negative sampling is a simple approach, I think is kind of safe approach, and that's how we fine-tune. For the distance function, I use the cosine similarity, but keep in mind there are different ways that you can solve the same problem. And to wrap, we have been using the elastic technology for semantic search. Okay, they suck. They are not built for this thing. And we have been trying to benchmark a few vendors, including Pinecone. And Pinecone is a company. Greg is here. You guys can talk to Greg. Pinecone is basically a vector database technology. That's how they built it. So we benchmarked these guys for a few months last year. And our plan is to walk away from Elasticsearch and use the Pinecone for our semantic search. And our hope is that we can go faster, we can iterate faster, and that scales hopefully down the line as we scale, because our content is kind of growing exponentially. So that's what we are planning to do in Q2, Q3, hopefully by end of Q2. We can improve the fine-tuning, but I think one major thing that we have planned to do improve to fine-tuning is that how we can sample hard negatives. This is another topic that you don't find much literature, practical things that you can really apply. And there are lots of papers in university. I have myself PhD, but many of the research work you would find that it's kind of useless. It's not really, you cannot really apply it, so people go and write papers, but they are not really thinking about the practical implication of the problem. But we have planned to programmatically sample random negative, and that way we improve, hopefully, the precision of fine-tuned model. There is an interesting paper called Unsupervised Sim-CSE, which is using a contrasting learning approach from image space, and they are trying to solve the computing embedding for sentences, taking an unsupervised approach, like how BERT was trained. So BERT doesn't use a supervised approach. That's the strong thing about it. My early, which is not surprising, my early benchmarking showed that unsupervised Sim-CSE underperformed compared to SBERT, which I'm not surprised because it's unsupervised. But the nice thing about that framework is that if you might be able to get to the level of SBERT if you fine-tune the, let's say, Sim-CSE, taking a unsupervised approach. So that's one other, I think, area for research that we might try this year. And last not least, we are hiring. We are hiring for search engineers, platform engineers, and ML engineers on the search and recommendation side. We also have a big NLP team. I'm not part of NLP team. I'm part of the search and recommendation team. But if you guys are interested, working for not social media company, I used to work for those companies, but for a company that really does something for education for kids, something that helps not optimizing clicks. So this might be interesting company/product for you guys to check. And that's it.
Thank you. So we already have questions online, and I'll kick it off with one. First question is, how was Faiss and sBERT used together? I think you mentioned that in one of your slides.
Sorry, can you repeat the question?
I think it's line 2 here. So how was Faiss and sBERT used together?
So Faiss is basically a paper published by Facebook for computing. So think of it as a alternative to LSH. So the way that we did this test that we ran was that we have this 400,000 Quora questions. So I computed the embeddings, SBERT embedding for all of those vectors, and then I've created index using Faiss. And for that, there is a library called AutoFaiss, which you can fine-tune your index parameters, and that's how we kind of created that index with Faiss. And the interesting part about this is that you see some improvement using Faiss versus LSH, but that was not significant, at least what I saw. There was improvement, but not big.
Questions from the audience here? Yep, of course, it's the last row.
Have you tried fine-tuning the transformer from scratch? No.
Quick one. We had another one up here.
Yeah, actually, I'll just follow up on his question because I had sort of the same question. You're focusing on fine tuning, as I follow, right, based on SBERT, and I don't remember what the total train time was for SBERT on its own. You know, so the cost of doing it yourself.
Training or inference time.
Well, I'm just because I'm thinking about the out of vocabulary question, right, and that's sort of the challenge. It seems like you're dealing with. Why not assess it against doing it off your own corpus from scratch?
So essentially, you want to also fine-tune BERT, you are saying, going deeper, and then, because we are using BERT, let me show again this architecture. So you see in this picture, this is how we fine-tune the SBERT. So still you are using BERT, and before fine-tuning, we still use BERT.
You train BERT on its own, like completely from scratch.
Yeah, we didn't do that. Yeah, we didn't do that. And for fine-tuning, it doesn't, for us, I think I fine-tuned with probably half of medium payroll questions, and on GPU, that didn't take long. Like, it was less than a day.
Yeah, because I would think you would want to understand what the base would be, like he's saying, if you did it off your own data from scratch, right?
No, I understand exactly what you're saying.
Go a step further, I'd say, the hell with BERT. I would actually use Electra, right? Because you want something that really is going to get a very deep understanding of your vocabulary, your corpus, right? I mean, transfer learning is great if you're just doing a casual case, but if you're so invested as you are in your own corpus, I'd be very interested to see.
Your point is valid, yeah. It's a very good point.
And also, I mean, I think that.
Oh, you can.
Sorry. To sort of think about this as well. I mean, so with the SBERT version you guys are using, I guess this is a question. You looked at the Quora data, you looked at some other data. Did you fine tune that SBERT yourself, or is that a Hugging Face model?
Sorry, can you repeat?
I thought, did you say that Did you say that the SBERT installation or the SBERT model you were using was specifically trained on some of that Quora data as well? Did you do that training?
Okay, so the way that, so our fine-tuning, for fine-tuning, yeah? So for fine-tuning, our approach was very simple. So essentially, that paraphrase MPNet-based V2 was the baseline model, SBERT model that you picked, and then I fine-tuned on top.
So potentially, I agree with the Electra comment, but also something that might be interesting to try is, so basically to make the paraphrase MNet base model, they took the SBERT model and they fine-tuned with the Quora data. So if you want to take your data and fine-tune in between those two things, so you take the SBERT base model, you fine-tune to your data, and then you fine-tune to the Quora data, that might be something to try, that might be interesting.
And what does that tell you?
Because then you are, we can talk about this a little bit offline.
Sure.
We have another online question. Do you have an intuition on how good Sentence-BERT works on shorter queries, for example, in e-commerce?
So I think, so let's say if your query is just iPhone, so I think it's obvious, longer your sentence is, more signal and info you give to the embedding. So more richer your vector would be. So shallower, I mean, less words you have, your vector is probably more sparse. So I don't think it's very hard to see that. So
Well, yeah, I guess the more information, the more words you have, the more information there is.
yeah.
Can I squeeze through here? Thank you. Thank you.
Yeah, I want to follow up on the last question. One can use the queries within the session to form a sentence, and then run the sBERT on the actually all queries that have been conducted within the same session.
Oh, so within a session, let's say I come and type my question. What you would do, what I did was that, let's say you came and you searched a query, and then you saw the semantic search results, and then you, let's say for that particular top results, you basically clicked and bought that. I sampled that as a positive pair. So, so you are saying that keep the whole user session and then sample from that user session for the positive pair? That's what you're suggesting?
Yeah.
Okay. I think the way that I sampled should probably cover that. The tough part, one tough part about this problem is, again, because you are using supervised approach, you are trying to create this data set of 100,000 pairs, and we cannot use human to label them. It's just, it's very hard to train human and get that. So how would you do this programmatically? So 80% of my time was spent on cleaning the data. That's a big part. The second part, and those are this non-sexy part that nobody talks about. You know, everybody comes, oh, look at me, I'm so great. And that was one challenge. This other challenge was this hard negative pairs that I just mentioned, because in our case, we sampled random negative, meaning that, you know, we paired two mass questions, but they might not be the example that I show you guys, and that's the nice thing about the Quora. If you look at their negative pairs, they are not very obvious. What are natural numbers? What is a least natural number? The topic is the same. I think this is important when you're trying to fine-tune, because it helps to improve the precision. So that's, I think, one area that someone can even publish a paper. How do you sample hard negatives? And in a programmatic fashion, obviously, not with human. That's obvious.
It was a wonderful talk. I just was curious, you know, as you're managing different search strategies, you have semantic, more traditional search. Does your team monitor which types of questions semantic search is performing really well for, or certain pockets that are weak? If you're comfortable talking about, like, kind of how you guys navigate that.
Yeah, so, no, it's very interesting. This question is an interesting one. So when you, let's say for semantic search, when you come and search a query and we have query understanding engine, which is kind of a bit outdated, we are going to improve that. We have lots of problems that we can optimize in our search. So we are using fast text for query understanding. When we detect the query is a question, we show that card on the top. And if you think from advertising point of view, when you push the ad to the top above the fold, it's going to have a huge conversion. So that's how you kind of move the metrics. So, but our federated search and semantic search, both of them get a lot of, lots of our, what should I say, revenue comes from our search. Lots of our traffic comes from, let's say, search engines, outside search engine, clicks, but most of our conversion comes from our internal search engine, which is Elasticsearch federated search, as well as the semantic search. But semantic search, if the intention of the query is a question, outperform federated search because of the way that you position, the position bias, again, last talk.
We have one more question online while I pass the microphone up there. So if a question is longer than 512 tokens, what would your approach be?
Good question. I think I did a benchmarking on the distribution of query length, and what I found that, which is, it's not hard to see, our distribution is most of our I think about 80% of our questions are under that threshold. So keep in mind, as you increase the length of query, the inference time increases. And I think that was quadratic in terms of tokens. So there is always cost. So, but that question, let's say if we have lots of documents, we want to create embeddings for documents, and a document could be 100 pages. So one simple thing you can do is that you can take each paragraph, compute a vector. Now you have a composition of vectors. Now that becomes even more interesting problem that nobody is working on, no vendor. So go and start your startup.
I may have missed this part, but do you have a topic or a category for each document?
Sorry, what do you mean?
Do you have some kind of taxonomy for the documents that you're searching? Or categories or topics?
We do have concepts.
Okay. Yeah, because I found that if you're searching for random negatives, you can do something like if you have positives, you can look within the same categories as the positives, but ones that aren't, clicked as positives, and that gets much better randoms because they're so closer to the query.
That's smart. Right now, the way that I sample random negatives, I sample within a subject.
Okay.
We have 40 subjects, but what you are saying even go deeper. Let's say
Yep.
if we have thousands of concepts. So let's say sample within the concepts because it's a hierarchical cluster. So that probably even improve.
Like I'll randomly pick a bunch of random, and then I'll train a model, and then every epoch I'll pick a different set of random ones, and it seems to, because then you want a lot of for every positive example, you want 10 or 20 negatives at least.
Yes.
Because
yes.
it's there's so many more negatives than there are positives, so you need to give it so much variety, and I found that really helps. But you also I think you do need the random negatives to bootstrap it.
So what would the ratio for you for positive and negative? What you found?
I'm not really fixing a ratio. I'm just every time I'm creating a random negative and a positive. Because the MNR allows you to pass 3 values in, so it's like query positive negative. Every epoch I'll train with a different random negative.
Okay.
Well, it's randomly sampled, so I'm not forcing it to be different, but it's likely to be different. And then training it for 5 or 6 epochs.
Yeah, that concept, within a concept, is an interesting one. That's it.
Yeah, because I tried picking the same category, and that didn't work. But if I start picking the same parent, I think that was far enough away that it worked well.
I haven't tested that, but I think that worth testing for sure.
But I tried triple loss, and that was terrible. But
Yes,
the MNR,
I tried triplet loss. What I found with triplet loss was that even more sacrifice on precision. So I didn't present. There are lots of hyperparameter optimization I have done, and I didn't present it here. And that's why I kind of decided to stick to the cosine similarity. But triplet loss improved the recall even beyond the cosine similarity. It was more aggressive in terms of improving recall, but precision was more sacrificed. So I thought that, maybe this is a bit, so let's go with the more conservative approach.
were you using both then, or just triplet loss?
For what we ship to production, I use the cosine similarity as distance function.
Uh-huh. But triplet loss is the loss function.
No, the loss
training.
function was cosine similarity loss.
Oh, loss. Okay.
But I tried triplet
Triplet.
loss too.
Because you can, with SBERT, you can also give it multiple objectives. So I considered trying a combination, but I haven't done that yet.
That's interesting. I haven't tried that.
But they support that. Like you can give it multiple data loaders with different objectives. As soon as you're using the same loss function, but it's just sampling differently, I think that would work well.
Okay, so last question.
How frequently do you plan to retrain this model? And coming back to your future plans about introducing the vector search, so do you guys foresee some challenges with respect to how frequently you want to retrain a model and reindex all your documents at scale while serving production traffic?
So in terms of the in the very early stage, so I just once, and we A/B tested. So we have planned to ship that to production to all indices. In terms of index, we have continuous indexing. So we have this backend processes that runs continuous indexing. So as the new questions come, add. So that's we had to. So our index keeps growing I think that continuous indexing probably runs every day. Yeah.
Okay, so thank you very much. And next up is lunch break till 1 o'clock. See you there.